Hello everyone. In this session we'll discuss about the different sequences of the stepper motors, and also we will see the implementations of these sequences in keil. Okay, so there are three different sequences that can be applied for a stepper motor in order for to make it rotate. So the first sequence is wave sequence, and second sequence is full step sequence, and the third sequence is half step sequence. Okay, so let us go with each of them. The first two sequences, wave sequence and full step sequence, will have 4 steps for every sequence. Okay, I'm sorry. Whereas the half step sequence, there will be 8 sequences for in the entire set of signal sequences. Okay, so let us go with the wave sequence first. Now in this wave sequence, the cycles are divided into 4 different cycles. The one is C1, C2, C3 and C4. The C1, in the time interval of C1, only a coil is excited and the rest of the coils are not excited. In time interval C2, at that time B coil is excited and the rest of the coils are not excited. In interval T3, C coil is excited and the rest are not excited. In the interval C4, only D coil is excited. Now let us assume that whenever a coil is excited, at that time that particular phase becomes a south pole. So now let us analyze what happens during cycle C1. Since A is excited, this particular pole, this particular coil becomes south pole. So the rotor will align in this position. Okay, and when B is excited, at that time the south pole will shift to the horizontal axis. So naturally the rotor, which is fixed fixed at this center, will tend to rotate in a clockwise direction by 90 degree. When C is excited, as in cycle number 3, at that time C becomes south pole and the rotor will further rotate by 90 degree. Okay, now when D is excited, then the south pole will shift back to the horizontal axis and the rotor further rotates by 90 degree. Now if we repeat the sequence C1, C2, C3, C4 indefinitely, at that time the rotor will keep on rotating in a clockwise direction. So this is one way of looking into the wave sequence. Now other way we can apply the sequence is, we just negate 1 0 0 0, 0 1 0 0, 0 0 1 0, 0 0 0 1. Okay, so if it is a common ground, if the common is the ground, then 1 0 0 0, 0 1 0 0, 0 0 1 0 and 0 0 1 0 0 0 1 are valid sequence. If the common is not ground, and if the common is VCC, at that time the valid sequence is 0 1 1 1, 1 0 1 1, 1 1 0 1, 1 1 1 0. Okay, so I repeat it. If the common is ground, then whatever we have in this table is a valid sequence. If the common is VCC, at that time the sequence is 0 1 1 1, 1 0 1 1, 1 1 0 1, 1 1 1 0. Okay, so these two are the valid sequences when it comes to the wave sequence. Now let us go to the next sequence, full step sequence. Okay, here the 4 phases are classified into x-axis coils and y-axis coils, and there will be a separate x-axis ground and y-axis ground. That means B and D are grouped as a vertical axis coil and A and C are grouped as a horizontal axis coil. Okay, so in this at any point of time 2 coils will be activated. Okay, that means to say one of the coil of the horizontal axis and one of the coil of the vertical axis will be activated. As you see in this table, in the first cycle A and D are activated, whereas B and C are not activated, okay, if it is a common ground. So that means to say, whenever the coil has a current passing through it, let us assume that it is a south pole. So that means to say this becomes a south pole, this becomes a south pole. So the resultant magnetic axis will be in between those two, that is 45° aligned to the x-axis. So whenever A and D are activated, or whenever they are excited, then the rotor will assume this position, which is 45° inclined to the x-axis. Now the next sequence after the first sequence is A and B being 1 and the rest being 0, 0. At that time, whenever A and B are 1, at that time the magnetic axis will be minus 45°. So the rotor, which was at 45° position, now tends to rotate to a minus 45°. So eventually making a turn of 90° between each of the sequence or each of the cycle. Further, it becomes 0, 1, 0, 0. At that time, B and C are excited, so the rotor will shift to minus 135°. And further, when C and D are excited, it becomes 0, 0, 1, 0. Then the rotor will shift further by 90° and assume the position of 135°. So if the sequences are repeated 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1, 1. If these sequences are repeated indefinitely, then the rotor will make a rotation continuously in a clockwise direction. Okay, now let us talk about half-step sequence. Okay, in this sequence there are totally 8 steps that forms a sequence. Okay, so now let us explore this particular sequence. The sequence, if you observe this carefully, the first step shows that the pattern of excitation in the first step is 1, 0, 0, 1. Second step is 1, 0, 0, 0. Third step 1, 1, 0, 0. Fourth step 0, 1, 0, 0, so on and so forth. Now if you observe the odd steps in this particular sequence, 1, 3, 5 and 7, that constitutes a full step sequence. Okay, and if you observe 2nd, 4th, 6th and 8th, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, that constitutes a wave sequence. So when you merge the full step sequence and the wave sequence, you will get a half step sequence. Remember earlier in the earlier sequences, the full step as well as wave sequences, that there were totally 4 steps in every sequence. However, here there are 8 steps. Okay, and in earlier sequences, the angular rotation for every step was 90°. Now here it is 45°. Now let us see the working of this particular sequence. Okay, let us see the stepper motor working when applied this particular sequence. Okay, when 1, 0, 1 is applied to A, so 1 and A and when 1, 0, 0, 1 is applied, A and D are excited. So basically the resultant magnetic field will be 135° inclined to x-axis. Okay, so the rotor will assume the position as shown in step 1. So in step number 2, only A is excited and the rest of the coils are not excited. So naturally the rotor will rotate clockwise by 45° and assume the position of 90° with respect to the x-axis as shown in step 2 of the diagram. Now further, the coil is excited as in step 3, that is 1, 1, 0, 0. At that time A and B are excited with 1 and 1 and C and D are not excited. So the resultant magnetic axis will be 45° inclined to the x-axis, hence the rotor will rotate further by 45°. So if you keep on repeating with this, if you see this, the rotor is rotating clockwise with an angle of 45° for every steps. So when you complete the 8 steps, the rotor would have completed a rotation of 360 degrees. So if you keep on repeating these steps indefinitely, or if you repeat the sequence of steps indefinitely, then the rotor will keep on rotating in a clockwise direction indefinitely. Now let me demonstrate the working of the wave sequence. Initially, let us say that we have loaded in register A value in binary 10001001, that is equivalent to 88 hexadecimal. So now if I shift this by 1 bit right, so it will be 01000100 binary, so that is going to be equal to 44 hexadecimal. Then further, if I shift that above by 1 bit right, it will be 00100010 binary, so that is going to be 22 hexadecimal, and subsequently it will be 00010001 binary, that is going to be equal to 11 H. Okay, now let us observe the lower nibble of all these 4 bytes. The first is 1000, another is 0100, third is 0010, fourth is 0001. So if we map D3 to A, D2 to B, D1 to C, and D0 to D, then A will be in the first step it will be A being 1 and the rest being 0. In the second step it will be B being 1, rest being 0, and the third step C being 1, rest being 0, and the fourth step it will be D being 1, rest being 0. So this is a classic example of a wave sequence. So what I'm going to do is I'm going to write an assembly program. Say start, okay, label. So first I will assign A with hash 88H, okay. Then I am going to assign port 1 with A, and the lower nibble of port 1 will be connected to the drivers, which will in turn drive phase A, phase B, phase C, phase D of the stepper motor. Now the driver can be a transistor based driver also, or any other drivers, okay. Now so in the first step I have assigned 88 to A, and then I have moved A to P1. Then I will just rotate right A, okay, and then call delay, right, and then I will say S jump loop, okay. So what I'm going to do is I'm going to assign this second line with the label of loop, okay. So what happens here? A call, let me use A call, okay. No harm if you use A call also, okay. Now if you see here, first A will be 88, it will be assigned to P1, and when you rotate right A, it is a cyclic rotate, so A will become 44. So then there will be a delay, then it will go back to the second line and assign 44 to P1, and further it will rotate A, so it will become 22, okay. So it will further delay, wait for some few moments, and then come back here, and it will assign 22 to P1, and then rotate A right through not through carry, okay, cyclic rotate. Then A will become 11, and then again A will become 88, so on and so forth, 88, 44, 22, 11, and the sequence will keep on repeating. Now let us write the loop, okay, delay loop, delay subroutine, sorry, okay. So the first statement in delay subroutine is we will assign R5 with the some value hash 0FFH, okay, and then subsequently we will also assign R4 with FF, okay, and then I say decrement jump on no 0 R4 R4 comma I loop OP. Okay, I loop stand for inner loop. Okay, basically I am cascading two loops here. I am using two registers and I am putting writing two cascaded loop. Okay, TJNZ R5 comma O loop, then RET. So what does this delay subroutine do? It will assign 255 to R5 and then 255 to R4. R4 will decrement from 255 to 0. Once it has decremented, then R5 will start decrementing. R5 will be decremented by 1 factor, and again R4 will decrement from 255 to 0. So basically this program will execute 255 into 255 number of times. So then I will say end and let me compile this project. Okay, and see if there is any error. There is an undefined symbol in 9. Okay, undefined symbol ILOOP. So 9 is undefined. What is this? Is the spelling right? Is it I or T? I loop, and then I'll say I loop, I loop, I loop, I loop, and this is O loop. Yeah, O loop. Okay. So again it points to number DJ and Z. Okay, I loop. Okay, yeah, this is 0, somehow 0 creeped in instead of O. You have to be a bit careful when you press O. If 0 creeps in, then it looks similar. That was the classic example where I could not identify whether what was the error. Then I saw that it was one was O and another was 0. Okay, so it has executed, it has compiled successfully. Now I'll go to the debug session and I'll open the logic analyzer. I have already opened the logic analyzer, and I have created I have mapped 4 pins P1.3, P1.2, P1.1 and P1.0. So let us run this program and see. Okay, the waveform. Okay, so if you see that if you see, let us say that the green pin maps to phase A, whatever green waveform mapped to phase A, and red waveform maps to phase B, and black waveform maps to phase D, and blue waveform maps to phase D. So if you see the steps, voltage levels in each of the step. Okay, in the first case it's A being excited. In the second step it is 0100, so it is B, coil B being excited, and step 3 it is C being excited 0010, and step 4 it is 0001. So coil C D is getting excited. I will repeat it again. Here A is excited 10000, and here 0100 B is excited. Here it is 0010, C is excited. And okay, so far we saw the example for wave sequence. Now let us talk about full step sequence. In full step sequence, I will put this as 99. Okay, let us now analyze the data. 99 is 1001, 1001. Okay, in binary. Okay, if I right shift by 1 bit, it is 1100, 1100. If I right shift further, it is 0110, 0110. And if I right shift further, it is 0011, 0011. So let me ignore the upper nibble, and now let me see the lower nibble itself. So in the first case, A is mapped to the D3, phase B is mapped to the D2, phase C is mapped to the D1, and phase D is mapped to D0. So it is A and D that is active in the first step, then A and B is active in the second step, B and C is active in the third step, and C and D that are active in the fourth step. So let us go back to our PPT and verify that. So A and D are active in first step, A and B are active in second step, B and C are active in third step, and C and D are active in fourth step. So it matches this. Okay, so let me run this, compile this and run this program. Okay, so when I run this program, let me plot the different waveforms of D3, D2, D1 and D0. Okay, so there we go. Let me stop it. Okay, 1001, 1100, 0110 and 0011. So the first step in the sequence is 1001, next step is 1100, next step is 0110, last step is 0010, and the sequence keeps on repeating again. So this is the 4-step full sequence. Okay, so now having this full step sequence, how do you generate half step sequence? Now we said that earlier, half step sequence is nothing but the combination of full step sequence as well as wave sequence. In full step sequence, our starting value is 99. Okay, whereas in the wave sequence, our starting value is 88. So I will hold 88 in one register R2. Okay, move R2 comma 88. So first we will assign 99 to P1. Okay, so and then later we will assign 88 to P1, and then we will shift both 99 and 88 right hand side twice. Okay, so I will move R2. Okay, so this one, so the program is complete. Let us discuss about this. Initially R1 is 99, R2 is 88. So 99 will be pushed to P1. So we have 1001, 1001. So this will be in P1, and after that 88 will be pushed to P1, or 88 will be moved to P1. Okay, and before that, if you see here, 99 has become CC. Okay, and the value of R1 is CC. Okay, then 88 will be moved to P1. So it is 1000, 1000. Okay, now when it waits for certain minutes, few seconds, that's decided by the delay, and goes back, R1 contains CC. Okay, so it is 1100, 1100, and then 88 would have got shifted earlier by 1 bit. It becomes 4. So it is 0100, 0100. So now it is 9, then 8, C and 4. So let us see that A and D are active, then A is active, then A and B are active, B is active. Let us see from our PPT from the half step sequence slide. So A and D are active, then A is active, A and B are active, and then B is active. So it is 9, 8, C and 3. So it is it is as expected. So let us compile this program and run this program. Okay, so there is already an attempt to define already. So let us go to 9 loop. So okay, let me remove this. Okay, I don't need this. Okay, there was a small error in the program, that's fine. Okay, now it's fine. Okay, so let me put the session in the debug mode and let me run the program. Okay, let us see the waveform. Okay, so let me come back here. A and D are active, then A is active, then A and B is active, then B is active, B and C are active, then C is active, then C and D is active, and D is active. I repeat it. A and D are active, A is active, A and B are active, B is active, B and C are active, C is active, C and D are active, and D is active, and it repeats. So there are 8 steps in a sequence. So it is a 8-step sequence or a half-step sequence. Let us see. So A and D are active, then A active, then A and B are active, B active. So let us verify the waveform. A and D are active, A active, A and B are active, B active, so on and so forth. So it matches what it is expected. Okay, what is expected out of it. Okay, so the observed results and expected results are matching, so the program is working fine. Let us now focus on the operation of DAC, as well as how to write a program for a DAC to generate a particular waveform. Okay, now so this particular slide gives you the interfacing between 8051 and DAC 0808. Now DAC 0808 is an 8-bit DAC. So all the pins of the DAC 0808 will be sourced from one of the port. So P1.0 to P1.7 will effectively give the digital input, and the digital input will be fed to pin number 5 to pin number 12, and the analog output will be obtained at pin number 4. Okay. Now you need to understand that DAC 0808 is a R2R network. Okay, so we will not discuss about what is an R2R network is. There are a lot of materials with regard to R2R networks available on the net. Okay, now let us see the operation of this. Now the output current is given as dependent on the reference current. The reference current is set using the reference voltage 5 volts and divided by the 2 resistor 1 and 1.5k. So in this case the reference current is approximately equal to 2 milliamperes. Okay, so if To start with, let us generate a ramp waveform. Okay, so let us add a assembly program to the source group. Add new item. So I'll call it as assembly file. We'll call it as ramp. Okay. Okay. So the way to do it is, I will first have an assembly directive start. Yes. Okay, and I will move a comma hash 00. Okay, then I'll say loop. I'll tell you why I'm doing this. Here I'm going to move a to p1, p1 comma a. Then I'm going to increment. The way I increment is, I can just say increment. Okay, no problem. inc a. Okay, and then I'll say a call delay. Okay, and then sjmp loop. Okay, so I'll define a delay subroutine here, delay. First I will put the value ff2r7 r7 comma, no, let us put hash 010. Okay, or hash 1010 hexadecimal. Then I will use another register r6. Okay, I'll explain this program. R6 comma hash 0ff hexadecimal. I'll call this as O loop. I'll call here I loop ILOOP DJNZ R6 comma ILOOP. Okay, then DJNZ R7 comma O loop, then RAT, then end. Okay, let us see what this program does. Okay, so initially A is assigned to A, then I'm going to move 00 to P1, then I'm going to increment A, so A will be now 1. So then I'll call the delay. Okay, this delay, there are outer loop and inner loop, so it will keep on counting, it keep on decrementing R6 till it becomes 0, and once R6 becomes 0, it will decrement R7, and once both R7 and R6 are equal to 0, it will exit from this delay loop, and then it will go back and assign 1 to P1. So if you see here, for every time period, it will keep on incrementing the value of P1. Okay, so let me compile the program. So the output P1 has got a linear relationship with time. Okay, so so it's equivalent to y is equal to ax. Okay, so that's the reason why it would generate a ramp wave. Okay, from 00 to 255. Once it crosses 255, at that time it will overflow and A will become 00. So naturally it is going to fall back from 255 drastically down. Okay, so let me compile this program. Okay, no errors and debug. Okay, while debugging, I will put the output of the logic analyzer to an analog mode. Okay, so let me bring up the logic analyzer, and let me set up the logic analyzer. Okay, set up, and I will set up port 1. Okay, P1. Okay, and the P1 I will put that in analog mode. Okay, it is in analog mode. The minimum is 0, maximum is FF. Okay, so the setup is done. So let me now run the project. So basically I'll have to put it in the debug mode, and then I have quit from the debug mode. Okay, let me go back to the debug mode again. Hopefully the logic analyzer is there. Let me run the program now. So it is you see that the value is increasing. So let me zoom out. So you can see the waveform generated by this logic, so basically it is increasing linearly from 0 0 to FF, and once it reaches FF, since it overflows, it will go back to 0 and start again from 0 0 to FF. So this is the program to generate a ramp wave using assembly. Okay, now let us see what happens when we increment a by some factor of 10. Okay, so what I'm going to do is I'm going to say, instead of increment, I'm going to say add a comma hash 10. Okay, so when I do this and when I compile this and run this, okay, build target and debug mode, let me run this. Okay, so let me stop this and let me zoom in. Okay, if you see, I can distinctly see that now it is not a smooth ramp wave, it is a staircase ramp wave. Okay, this is because when I increment the digital value by a factor larger, then the resolution keeps on changing. Okay, so the waveform will not be smooth. Okay, so now with that, let me go to the program back and let us change this ramp wave generation to a square wave generation. Okay, so I'll say CPL A. Okay, so what it does is this particular program, it will assign 0 0 to port 1, and then it will complement 0 0 to FF. Okay, and it will wait for further delay. So I will introduce more delay in this case. Okay, and let us now run build this project. Okay, let me explain this program. Initially 0 0 will be assigned to P1, and then 0 0 will be complemented. When you complement A, it becomes FF, and then the port 1 will be in the state 0 0 for some delay, and when it comes back, port 1 will be assigned FF, and it will wait for some times, and by that time A would have changed to back to 0 0, and so it will keep on executing this program with port 1 being port 1 alternating between 0 0 and FF. Okay, now let us build this program, and let us set the session to the debug mode. Okay, and run the program. Okay, let me stop this and let me do the setup. Okay, setup, I have to choose analog. Okay, now let me run this. Okay, so I see that initially it is 0 0, and then it will be complementing A. So let's zoom in. Okay, it's consistent throughout, so there is some problem with the program. I am setting 0 0 and I'm moving to A, then I am complementing A. Okay, I don't need this command. Okay, let us try it. Let us compile it again. So build and no errors, go to the debug session and then run the program. Okay, and then zoom out. Okay, so stop. Okay, so this program has generated the square wave as we have expected. Okay, let us extend this program to generate a sinusoidal waveform. Before you write the program, for the sake of for generating sinusoidal waveform, we need to work with sampling concepts. Okay, because a sinusoidal waveform is not a linear waveform, so we need to get some samples of sinusoidal, and we have to keep on dumping the samples of sinusoidal or the amplitude of this sinusoidal wave samples, and we have to plot the sinusoidal with respect to the time. Okay, so let us consider that let us consider 12 samples in a waveform. If we consider 12 samples for the entire period, then each of the samples are separated by a distance of 30 degree, because 12 samples correspond to 360 degree. So two of the samples are spaced at a distance of 360 divided by 12, that is 30 degree. Okay, so let me open the Excel sheet. So if there are 12 samples, then if the first sample indicates the angle of 0 degree, then second sample is spaced at 30 degree further, and third sample 60 degree, fourth sample 90 degree, so on and so forth. So now if I calculate 128 plus 127 sine theta, so when theta is equal to 0, it's going to be 128. When theta is equal to 30, it's going to be approximately 191. So for the rest of the values, we have calculated. For rest of the theta values, we have calculated the function values here. The function is 128 plus 127 sine theta. Okay, so we will take these values and use in our assembly program. Okay, so let me copy this and go back to keil. Okay, and I will define a assembly directive called as sine. db define byte. Okay, then I will use all these values. Okay, okay, so I'm almost there. Okay, so now the samples have been taken. Now there are 12 samples, so I will initialize a value called as initialize the value 11 to R2. Okay, so 11 is nothing but 0B. Okay, so the first thing that I'm going to do is I'm going to initialize R2 to 0B. Okay, and then I'm going to initialize dptr. Okay, the dptr comma hash sine. Okay, so let it contain the starting address of the data. Okay, so dptr is now pointing to 128. Okay, so then I will move the content of dptr to A. Okay, then I will move it to port 1. Then I am going to clear A. Okay, so before I clear A, I'll say move. This is wrong because I have to use index addressing mode because this data is in the code segment. So at the rate of a plus dptr. Okay, this is right. Okay, so first I will initialize r2 to 11, and then I will assign the first value of the data to dptr. Then I am going to use index addressing mode and move the data from start moving the data from this to a, and then I'll move it to p1, and then I will clear a. Okay, once I clear a, I will call I will increment dptr, then I'll say jump on no zero, jump on I'll call the delay function. Okay, and then I'll say jump decrement jump no zero r2 comma loop. Okay, and then sjump start. Okay, let me explain this program. First I'm going to move 11 to a, then I'm going to move the starting position of this data to dptr, then I'm going to move the first data, then I'm going to send the first data, clear a for further processing because I need to use a as an index for the next index addressing mode, and then I'm going to increment dptr, then I will call delay, then I will decrement. So basically there are 12 data, so I have to decrement, I have to execute this loop 12 times. Okay, and then once all the data are exhausted, I will repeat this particular process of putting this data back to port 1. Okay, so after that I will go back and repeat the cycle again and again. Okay, so let us compile this, and let's see if there is an error. No error. Okay, good. So then I will go to the debug session and simply run the program. Okay, and I'll zoom out. Okay, so now we can see step sine wave. Why we are seeing the step sine wave? Primarily because the number of samples are 12. Okay, so that's the reason we are seeing the step sine wave. If the number of samples were more, like 48 or 64 or further, the more the number of samples, the more smooth this waveform will tend to become. Okay, so since the number of samples are less, so you see the stepped sine wave in this particular output.